Hello friends, welcome back. In this tutorial, we will learn about I/O ports or input-output ports. Microcontroller by itself is a useless device unless we connect some peripheral devices with it. It can perform numerous arithmetic and logical operations at a very short time. For example, it requires less than a microsecond to perform addition of two characters. But to perform these operations, we need to provide it with some input data, and similarly, we need a way to show the output results. Thus, we need I/O ports. Think of your computer CPU. You need keyboard, mouse, or other input devices to provide data to the CPU, and monitor, speaker to see the results. Similarly, for microcontroller, input devices can be a switch, a keypad, or a sensor. Output devices can be a simple LED display, a 7-segment display, or a graphic LCD. Now let's have a look at the pin diagram of ATmega16 microcontroller. It is a PDIP package. As you can see, it has total 40 pins, 32 of which can be programmed as input-output pins. These pins are programmable. You can either set a pin as input or as output pin. All the input-output of AVR microcontrollers are divided into groups. These groups are called ports. Each port consists of 8 input-output pins. Thus, ATmega16 has total 4 ports labeled as port A, B, C and D. There is an important advantage of grouping the pins into ports. As ATmega16 is an 8-bit microcontroller, it can perform any operation of 8-bit data at a single clock cycle. So we can read or write values of 8 pins at a single clock cycle. This will increase our processing speed. Each microcontroller has some registers inside the chip which are used to configure various modules of the microcontroller. For example, each input-output port is associated with 3 registers. Here you can see the registers only for port A. The DDRA register is used to set the data direction of each pin in port A. The port A register is used to store the values of the output pins, and pin A register is used to set the values of input pins. Here is a simplified block diagram of the input-output circuitry of each pin. Each pin requires 3 bits to configure it completely. The DDXN bit comes from the corresponding DDRX register, port XN from port X register, and pin XN from pin X register. You can see the datasheet for ATmega16 to see the detailed circuit diagram of each pin. This is a tri-state buffer which simply acts as a switch depending on the signal on DDXN bit. Now we will see how we can send some data to the output device and read some data from the external input devices. Here I have connected a LED to the pin 1 or PB0 pin. To set the pin as output, all we need to do is to write logical 1 to the 0th location of the DDRB register. The buffer will be on, and whatever the value at port B0 will appear at the pin 1. Then if we write 0 to the 0 location of port B, we will get 0 volt at pin 1 or PB0 pin, and the LED will be turned off. Similarly, if we write 1 at the same location, we will get 5 volt and our LED will be turned on. Thus we can see how the values of port B register can be used to send some output value to the external devices. Now we want to use the same pin as input pin. We can do this by writing 0 to the DDB0 bit. By default, all the bits in DDBR register is 0. Therefore, all the input-output pins are initialized as input pins. The register with the switch is called a pull-up register. If you do not connect this register, you will get a high impedance state when the button is not pressed. But we don't want that. We want logic 1 when the switch is open and a logic 0 when the switch is shorted. Here we see that when the switch is open, we will get a logic 1 in pin B0. Now, if we press the switch, we will get a logic 0 in pin B0 bit. Thus, we can easily read the input devices by reading the pin B register. To make it simple, there is already an internal pull-up register inside the chip. This register can be enabled by writing logic 1 to the corresponding bit in the port X register. So we can see that the port X register has two functions. It can be used to store the output values for output pins, and at the same time it can be used to enable the internal pull-up register for input pins. If we use mechanical switch, then we will face contact bouncing problem. As a result, instead of single transition from 1 to 0, we will get a rapid pulse of ones and zeros. To reduce bouncing, we can use either software debounce or hardware debouncing circuit. We can use a simple RC circuit whose time constant is larger than the bouncing time. There are many improved debouncing circuits which utilize latches or Smith trigger. To use software delay, we will use simple delay function to avoid bouncing time. We will deal with the software debouncing later in this tutorial. Here is a summary that we have learned so far. Try to understand this before proceeding further. Now that we have know how to set input-output pins, we can move forward and do some coding. I will assume that you know bitwise operation and know how to set or clear a single bit inside an 8-bit register. Otherwise, refer to any C language book. First example shows how you can set the entire port C as output port. Next example shows how to set only PC0 and PC2 pin as output pin. And the last example shows how to read an input pin assuming a switch is connected at PC1 pin. Now I will show you how to implement a simple LED chaser using input-output ports. Here 8 LEDs are connected to port C and 2 switches is connected to PA0 and PA1 pin. These are active low switches, means we will get logic 0 when the switch is pressed. Internal pull-up registers for these switches are enabled. Now let's run the program. You can see how the LEDs are turned on and off one at a time. Initially one LED turns on after another at 100 milliseconds later. Now if you press the button at PA0 pin, this delay would increase and our LED chasing will be slower. Similarly, if you press the button at PA1, the delay will decrease and we will get a fast LED chaser. Now let's open AVR Studio 5 and see the code for this program. Here we have defined the macro fCPU to be equal to the system clock frequency, which is 1 MHz in this case. UL means unsigned long integer. You should define this macro if you use the delay.h library file, because the function inside delay.h requires that this macro is defined. The delay.h library file helps us to generate software delays. It has two functions, underscore delay underscore millisecond and underscore delay underscore microsecond. Both functions require constant values as argument. You cannot provide a variable as argument to these functions. Therefore, we have defined the wait function that will generate delays depending on the variable d. Here, delay millisecond takes constant 10 millisecond as argument. The header file io.h is a common header file for all of your projects. Here the address or locations of all the registers inside the chip is defined. For example, the address of DDRC is 14 in hexadecimal. You do not need to remember this address. DDRC macro is already defined to have this address. You can see the header files on the Solution Explorer. For ATmega16, the iom16.h file contains the macros of register address and bit locations. Now let's see the main function. First, we have declared the port C as output port by writing 1 to all the 8 bits of DDRC register. The next line is a bitwise clear operation, but by default all the bits of DDR register is 0, so this instruction is not necessary. Next, we have enabled the internal pull-up registers by writing logic 1 to the corresponding bits of port A register. This is a bitwise set operation. The I variable is used to determine which LED will be on, and direction or dir variable is used to define the direction of the LED chaser. The delay variable contains the delay time in millisecond between the two successive LED on state. Next is the infinite loop. This endless loop is used because there is no operating system in the microcontroller to return to. So microcontroller keeps running until the power is removed. Inside, the if condition is used to check if the switch at PA0 pin is pressed. If the switch is pressed, then the microcontroller will wait for 20 milliseconds. This delay is required to avoid bouncing problem. This is a very basic software debouncing. More advanced software debouncing can be implemented using timer counter. If the if condition is met, then we have increased the delay time up to 1 second. The same logic is used for PA1 pin, but here we have decreased the delay time. The next instruction turns on only one LED at a time depending on the value of I, then wait for a period defined by the delay variable. So this is the whole code for our LED changing program. Next we'll compile the program and burn the .hex file. To simulate this code in Proteus SS, first we draw the circuit in Proteus, then locate the hex file that we have already generated by compiling our program.